wrong, because really all we're doing is adding whole numbers. There is no way to wind up with a decimal or fraction with this. In this case, if the common ratio is a decimal, hang on, this is going to, half of 59 is 29.5, so that's
29524
29,524 times 15. Thank you, Lauren.
That doesn't seem quite right somehow.
It is.
My calculator says it is.
Just under 30, just under 60.
Well, yeah, but the wow.
Yeah.
I thought it said 254 instead of 524.
Okay, 400 and what?
442,860.
860. Who would rather have found this by adding up, for figuring out the first 10 terms and adding them without a calculator?
Joking.
Right. So it's a cool party trick. Okay, now that's actually not the cool thing I was going to show you.
I bet you do that at party trick.
I have a fun trick to show you.
Okay.
Let's all gather around the board and do math.
Is that like that trick right there?
No, it's no. This next one I think is cooler than that. Okay, actually I'm going to do 2 more examples first, and then I'll pull out the new party trick.
A number by 2.
What? There's another party.
Okay, Steven, I don't have quite a. He can read it on his own.
There's another part of this.
Well, yeah, I just want to show you how interesting it can get. For example, I think I can combine this into one example. If I say a sub n equals 10 times negative 1/2 to the nth. This series gets really annoying quickly, because a sub 1 is going to be negative 5.
Why?
10 times negative 1/2, because negative 1/2 to the 1 is itself.
But don't you have to do exponents first before you multiply?
I did. I said it wrong, actually. Yeah, I should. I should say negative 1/2 to the first is negative 1/2 times 10. In my head, I was doing it right. Came out wrong. A sub 2, negative 1/2 squared, is positive 1/4. So the second term is actually going to be positive 10 over 4, or 2.5.
No.
Yeah.
It'll be, oh yeah, 10 over 4.
It won't be 2.5, it'll be 10 over 4.
No, I thought you were...
No, please do double check me. You often catch me, and I appreciate it.
No, I thought you were trying to like cross it out, like make it smaller, and then you left the 4 on the bottom, but I didn't think that you...
Understood. The next one, the pattern of multiplying by 1/2 is predictable. You can go ahead and count on that. So the next one is going to be 1.25. But because at this point we'll be raising negative 1/2 to the 3rd power, it will be negative. Okay? A to the 4th will be half of this, which is 0.625, but it'll be positive. Okay, this is what, if you want about something that'll give you a headache quickly, if I said find the sum of the first 4 terms, it'd be negative 5 plus 2.5 minus 1.25
It'll totally be 1.
plus 0.625. May turn out to that. Eventually. But
That's annoying.
well,
Can we just use that?
we can do that instead, sure. And this time, so the sum is going to be the first term, negative 5, 1 minus r to the n. In this case, my common ratio is negative 1/2, and it's the first 4 terms, so it's 4th, over 1 minus my common ratio, which is negative 1/2. Have I plugged that in correctly?
Yeah.
Please double check me. Okay? So now this is going to be negative 5 times, alright, negative 1/2 to the 4th,
Is positive...
positive 2 to the 4th, 1/16, right?
2 times 2, yeah.
Okay? Negative 1/2 just by itself, subtracted becomes positive, is 1 plus 1/2. Am I good so far? Okay? So then this is negative 5 times 15/16 over 3/2.
Yeah.
Dividing a fraction by a fraction means I'm multiplying the 2 fractions. So this is negative 5 times 15 over 16 times 2 over 3. Reduce from here to 1 over 8 and 5 over 1. And I am getting that the sum is negative 25 eighths.
Yeah. Wait. Where did you get the 15, 16 from?
1 minus 1/16. I would have to make 1 into 16 over 16, and then subtract the fractions, which should get me 15 over 16. You guys always get tripped up on the 7th grade stuff.
Thank you.
And
It's not just you, everyone does.
It's confusing.
Well, the problem is while learning all the Algebra 1, Geometry, and Algebra 2 needed to survive this course, you weren't reviewing your 7th grade fractions.
Yeah.
And even when I'm teaching those courses, I don't always have time to slip it in. So you see how these geometric ratios can get more interesting than just doubling or tripling. Negative signs in fractions make them very interesting. Now,
That so did not equal 1.
hold that thought though.
Great.
It's going
You
to be
said it would
relevant right now.
eventually.
Great.
All right. It's a legendary conversation between, I believe it was Pythagoras and from Plato's Republic. Is it Plato's Republic? I'm not sure.
Of course.
Lost track.
Don't care.
Did
It was
Pythagoras make the Pythagorean theorem?
Plato.
Yes, but that's a little bit misunderstood.
Okay, just wondering who his name.
No, it does make sense. The ancient Sumerians actually had figured out like 3, 4, 5 triangles. And actually the Egyptians had figured it out before the Sumerians. But they've got clay tablets of like saying 3 squared plus 4 squared equals 5 squared. 7 squared, what are the other ones I told you guys to know that I'm suddenly... 7, 12, 13. 7 squared plus 12 squared equals 13 squared. I give you 9, 40, 41.
I thought it
And
was
all their
5,
multiples.
12, 13.
5, 12, 13. Thank you, you're right.
Yeah, that's what I was wondering. What?
The
Not
ancient
7.
Sumerians had figured those out. Pythagoras proved it's always true, and he started exploring the deep weirdness behind irrational numbers. He was the one who said it's even true if you have 1 here and 1 here in a right triangle, and this has to be the square root of 2.
Yeah.
And the fact that the square root of 2 is a never-ending, non-repeating decimal is what started to drive Pythagoras nutty.
Oh, okay.
Another thing, I mean, that's...
Doesn't it drive everyone nutty?
Well, think about it. I mean, you can't even do you can't even figure out the diagonal of a 1 foot by 1 foot tile without hitting truly bizarre math concepts.
Well, and then for him, he didn't even know, so he kept on going and going until he thought maybe there would
Actually,
be an end.
he absolutely proved it could never end using just fraction notation.
Ew, that's
It's a crazy proof. It's one of those elegant proofs in human history. It's brilliant.
What
I'll
makes
show it to you
it
sometime.
elegant?
The fact that it didn't take like 57 pages.
Oh.
You could actually do it in half a page.
That's awesome.
And it proves that the square root of 2 must never end as a decimal.
Not now.
Not now, but I will. I'd have to reread it over the weekend, actually. But I'll bring that in and show it to you. Here's another one, though, that